When you're a kid, you're told that all the stuff around you is made of atoms, and that atoms are made of protons and neutrons and electrons. And if you're lucky, you're told what protons and neutrons are made of. They're made of 3 quarks each. But if they're both made of quarks, how are protons and neutrons different? You're not usually told this as a kid. And you're not usually told what quarks are, and why they're called quarks when they're clearly spelled quarks. So protons are made out of 3 quarks. That's the first lie you're told. Protons are not that simple. At any given time, the proton will have 2 up quarks with charge plus 2/3 and a down quark with charge minus 1/3, which of course all add up to +1 because that's the charge of the proton. These 3 quarks are known as valence quarks, and they're definitely there. But the proton could have an additional up quark anti-up quark pair. An anti-quark is the antiparticle of a quark. And it could have other types of quarks, pairs of strange quarks and anti-strange quarks, charm quarks and anti-charm quarks. In fact, the proton likely has tons of quark-antiquark pairs. But there's more. The quarks are held together by the strong force, which is carried by particles called gluons. So inside the proton, there are zillions of gluons and quarks all zooming around close to the speed of light and colliding and annihilating, and new ones are forming, and it's a crazy raging party, such as the quantum world in a proton. Wouldn't that violate some kind of conservation law if particles just appeared in the proton? Quarks can and do just appear and disappear, but not out of nothing. Einstein's famous equation, E=mc², means that mass can turn into a lot of energy, or a lot of energy can turn into mass. In fact, the quarks that comprise a proton only make up 1% of the total mass of that proton. That's like saying I dropped some quarters in a bag, and suddenly it weighs 10 pounds. There's a lot of energy in all the motion of those crazy partying particles. And there's energy in the gluon field. All of this energy contributes to the mass of the proton. E=mc². All we need to conserve is the total mass energy of the proton, and nothing is violated as quark-antiquark pairs pop in and out of existence. But there are a few other constraints. The total number of up quarks must be 2 more than the anti-up quarks, and there must be 1 more down quark than anti-down quarks, so that the valence quarks come to a total of 3. And the quark-antiquark pairs of other types must all cancel out, like the top quark, and the charm quark, and the strange quark, and the bottom quark. When quark pairs spontaneously appear in the proton, other properties must be conserved as well, like charge. So if a quark with charge +2/3 appears, its partner must have charge -2/3. And the spin of the particles must be opposite, and the colorlessness of the proton must be conserved. This is cool. Quarks all have color, except it's not like real color. Color in quarks is a type of charge, like the electric charge, except instead of the electromagnetic force, it corresponds to the strong force. Quarks can be red, green, and blue, like the 3 primary colors of light. And when you mix those colors, you get white light. So when I said that protons are colorless, that means that their 3 valence quarks must be red, blue, and green. So clever. The quarks can change color, but the overall color has to stay white. It turns out that the anti-quark has the opposite color. So that would be like anti-red, which cancels out red. But I think the most amazing thing about quarks is that we know all of this about them without ever directly detecting one. In fact, you can never detect just one because they're never found alone. The more you separate the quarks, the more energy you have to put in to pull the quarks apart. And as you do so, you eventually put in enough energy to make up the mass of 2 new quarks that can then bind to the original 2. So next time you're told there are 3 quarks in a proton, there are 3 valence quarks and a sea of other quarks. Too many to count. Impossible to count. No, really, we can't like take a snapshot. Now